We'll be starting in 5 minutes. Hello, sir. Welcome to the meet.
Hi, good evening. This is Anjan Roy.
Good evening, sir.
Yeah, so this would be a audio recording or a meet, or how would you like it to be done?
Anyway, you're comfortable, sir. If you're comfortable with keeping your video on, it'll be a pleasure. If you aren't, even that will be okay.
Yeah, I could keep the video on.
Yes, thank you, sir. We'll be starting in a couple of minutes.
Yeah, should I get the video on?
You can start the video at 6:45, or we'll just inform you when we are starting the
Okay.
event.
ये दरवाजा भी बंद रखेगा, कोई नहीं आएगा. हम वीडियो कॉल में है, कोई भी नहीं आएगा यहाँ से. इधर इधर भीतर दिख से बंद होता है.
Today we have. Oh, okay. Can you hear me?
Sandra, we can hear you. Not yet.
Okay. Okay. Today we have his brother, Mr. Anjan Roy, who will tell us more about him. Over to you, sir.
Yeah, good evening. I'm Anjan, the younger brother of Ranjan Roy. I would like to thank Professor Cherian and the Physics Society of St. Stephen's for inviting me to say a few words about my brother, who was a bright young mind like all you students of the physics department. Ranjan studied physics in Stephens in the mid-80s and doing his MSc from IIT Kanpur, which he did not complete, and moved on to JNU to study MA Economics. Thereafter, undertook to teach final year economic honors in Hindu College. His reason for changing track is both inexplicable and fascinating. To cut a long story short, he had notions of doing something tangible and meaningful, wanting to make a difference in the life of those less fortunate. Those of you who may be interested to know a bit more about the brief life of Ranjan would check out a small fun book written by me, Where Do the Stars Go? It's available on Google Play, Play Store, Amazon Kindle, etc. My warm welcome to Dr. Richard Marchand, Department of Physics, University of Alberta, Canada, who I am given to understand would be the main speaker for the Ranjan Roy Memorial Lecture Series today. As a layperson, I am eagerly looking forward to listening to Dr. Marchand, most of which I am sure I would not be able to comprehend. I wish you all a very safe and a happy year ahead. Thank you.
Thank you, Mr. Anjan Roy. Okay, I would also like to thank our HOD, Dr. Jacob Cherian, for inviting Mr. Anjan Roy for this talk. Thank you, sir. Also, today we have amongst us Ranjan Roy's classmates who knew him from Stephens, IITK, and JNU. So we welcome you for your presence here too. Before I move on to introduce the speaker, there are some rules we have to follow during this lecture, so I'll state them. First of all, do remain muted during the entire lecture session and refrain from asking any questions. You will have an opportunity to ask the questions during the Q&A session which follows after the lecture. During the Q&A session, please type your questions in the chat box and I will forward these questions to the professor. Questions and refrain from typing anything that is unrelated to the topic. Questions from both YouTube and Gmeet will be considered. Now I will introduce our speaker for today's session, Dr. Richard Marchand. He is a professor of physics from the University of Alberta, Canada, whose main research interest lies in computational physics, spacecraft interaction with space environment, ionospheric and magnetospheric physics, structured and unstructured meshes, and more. He had obtained his bachelor's from Montreal University, master's from University of Toronto, doctorate from Princeton University, and finally postdoctorate from University of Maryland. He is at present a member of the American Physical Society, American Geophysical Union, and the European Physical Society. He is also the book review editor of the Canadian Association of Physicists. Without further ado, I would request Dr. Richard to start off the talk.
Thank you very much for this nice introduction. But before going on, I'd like to make sure that you can hear me, because sometimes I have difficulty with the sound in these video conferences.
So we can hear you.
Oh, okay, great. Thank you. So my name is Richard Marchand, and I'm as the introduction stated, I am a professor at the University of Alberta. In addition to teaching, I do research in the general area of space physics. And recently, in the last several years, I've been interested in improving inference algorithms or techniques for interpreting probe measurements or particle sensor measurements in space in terms of useful plasma parameters or physical parameters. So I will start with a very broad overview, an introduction, and let's start with nothing else than the whole universe. This shows a picture taken by the Hubble spacecraft or telescope. And
Excuse me, sir.
Yes?
I don't think you are presenting anything.
Oh, yeah, that's right. It's good that you noticed. Anyway, I won't start the intro. Present. Whoops. Let's see. It happens sometimes because I am teaching remotely, as probably all of you as well. And well, now let me know if you see my presentation. Can you see it?
Yes, sir, we can see it.
Okay, great. So I won't repeat what I've already said, but so the whole universe is not there because this is just a very, very tiny part of the universe. But all the dots that we see in this deep field view taken by the Hubble telescope is actually a galaxy, not a star. And it's just mind-boggling to see all these worlds that we will never explore, of course, but we can just imagine what's in these galaxies. Some of them are larger than our own galaxy. A lot of them are smaller, but it's just incredible the amount of I don't know. I don't want to say life or because we don't know, but of discoveries that could be made if we could just go there. Um, so yes, okay. So our galaxy. So I started with the whole world. Now let's get closer to home. And our galaxy is very similar to our sister galaxy Andromeda. It has approximately 100 million stars and lots of solar systems. Stars with there are several stars with planets, and we were just starting to discover these solar systems with planets and possibly planets in habitable zones of their stars. Um, the Our galaxy is depicted here. It's of course it's not a picture. It's not nobody saw it from that far away, but the sun is found to be approximately relatively at this distance from the galactic core, and I assume that you can see my cursor, right? The sun, the galaxy is not static. Of course, it's made of stars that are rotating, and it takes approximately 200 and some million years for the sun to go around the galaxy, just one revolution. And the disk of the galaxy is not perfectly thin. It has a certain thickness, and there's a potential gradient across the disk, which causes most of the stars that are orbiting around the core of the galaxy or around the center of the galaxy to have a periodic motion up and down. It's not just the trajectories are not in a plane, but it sort of oscillates up and down as it goes around the galaxy, and the period of oscillation is approximately 26 million years, which is interesting because we've been going up and down twice, a little bit more than twice since the extinction of the dinosaurs, some 67 million years ago. And our sun is traveling at supersonic speeds in the interstellar medium, and then this creates a bow shock, which is the transition region between supersonic flow and subsonic flow, and there are various parts of the heliosphere and termination shock, etc., that I'm not going to discuss. But there are some structures there that we can't see with the naked eye, but those structures can be identified with satellites, and in particular with the Voyager 1 and Voyager 2, which have been reaching much farther than what this illustration shows. And this shows the evolution of our sun. It's interesting. It started with just a cloud of gas in space, which condensated or collapsed under its own gravity, and then it ignited nuclear reactions, and ever since it has been relatively stable, but it is getting brighter and brighter as it evolves in its life. And this is where it is approximately now. Eventually, it's going to become a little bit brighter. It doesn't show, it's not obvious that it's going to be brighter at this point, but it is going to be brighter. And then eventually it will become a red giant, and that will be the death of our star. But we have lots and lots of time to think about that between now and the time when it happens. No, the next one, and here's another one that I find troubling and interesting. This shows the luminosity of the sun as a function of time. And initially, the luminosity was very low when it condensated from a cloud of gas in space. And then the luminosity has been steadily increasing, and this is where we are. Everything is normalized to what we know now. And in approximately 500 million years, right there, the increase in luminosity is going to be by, my guess is that it's maybe 50%. Or close to 50%. It's difficult to say on this illustration, but for sure in 2 billion years it will be significantly brighter, and between now and then all the atmosphere, I don't want to scare anyone and give you nightmares, but well, we won't be there ourselves, but something is going to happen at some point between now and then. But at some point, the atmospheres, well, the atmosphere on Earth will evaporate. It will just be eroded by the solar wind, and I'll explain a little bit why that will happen. Although I'm not a geophysicist myself, I talked to some colleagues of mine who are geophysicists and who study these phenomena. And the oceans will evaporate, they will just be lost, and our planet is going to be just like Mars, a very dry planet with a very tenuous atmosphere, and probably that there won't be any life left on the planet at that point. Okay, so the sun is the main driving force of our of our space environment and space weather. As you probably know, there are cycles in solar activity, and these cycles are characterized by a period of approximately 11 years. It's actually 22 years. It's twice the period that is often quoted, and it corresponds to changes in polarity in the magnetic field of the sun. Although the sun is not a dipole, but it has roughly a polarity, a magnetic polarity. And there are periods when it's very active, periods where it's very quiet, and the dangerous periods, as far as we are concerned, and our infrastructure in space and even on the ground are concerned, the dangerous parts are when it's very active, because then it can release flares and coronal mass ejections. Coronal mass ejections are just a big mass of plasma that is thrown out in space in a certain direction. It's not ejected in all directions, in all 4 pi steradians. It's fairly focused in a certain direction. So the chances of being hit by one of these coronal mass ejections are small, but when we are hit, and it has happened in the past few times, then the damages can be considerable. So here's a historical view of the solar activity, and the solar activity is characterized by the number of spots on the sun, and these spots on the sun have been observed for centuries now, but it's only relatively recently in the 1700s or so that people were starting to count them more systematically and more accurately. And when we hear that we are in the 20-some cycle of solar activity, it all starts from this one. This is the first one, second one, third one, etc. So you can figure out which cycle we're in at this time. And these numbers of sunspots on the sun that are relatively easy to observe, although not with the naked eye, it's not recommended. There's a strong correlation between these numbers of spots and the activity of the sun. And here's another one that shows this. And there's a proxy to the number of sunspots on the sun that we can observe on the surface of the sun, and this is the so-called F10.7 line radio flux that can be measured from the ground. And there's you can see here that this is the number of spots on the sun, and the flux of the f10.7 centimeter radio signal that we get from the sun all the time, except of course when when the observatory is on the night side of the Earth. But when the sun is visible, then we can measure that. And the advantage of measuring the f10.7 centimeter line is that it goes through clouds. So it's not necessary to actually see the sun visually. We can measure that even when it's cloudy. And this signal, this proxy, has been used for a long time now by different space agencies and space weather services to predict or to assess the risk of solar storms and magnetospheric storms. Okay. So here's an illustration of a coronal mass ejection. The sun is hidden by this screen here on a satellite, and so the sun corresponds to this white circle. And when there's a coronal mass ejection, it's visible from the satellite, and it looks like this big bulge of plasma that is propelled at really high speed in the interplanetary system. And if a planet happens to be on its path, then especially the Earth, then there can be considerable damage. Let's see. Okay, so closer to where we are, we have this is another ground picture of the solar system. There's the Oort cloud, which is here. It's very far from the sun, something like 5,000 astronomical unit. An astronomical unit, for reference, is the distance between the sun and the Earth. This is one astronomical unit. It's approximately 150 million kilometers. So that's 5,000 times that distance. This is where we have this Oort cloud. It's made of rocks and large pieces of ice that are sort of orbiting around the sun, but not in a disk. I mean, there's a disk-like structure, but it's largely out of the disk. Closer to the sun, there's this Kuiper belt, and that is a disk. This has a disk shape, and it overlaps mildly with Pluto, the former planet, which has been downgraded to a dwarf planet. And eventually, or not eventually, but every once in a while, one of these rocks is diverted, and it can enter the inner solar system and crash on planets, on the Earth in particular. Okay, and here's now, this is really close to home. This is the Earth magnetosphere. It's an illustration of the Earth magnetosphere. It has all these components and parts. It's almost like looking at a cell in a biology textbook. There's the Earth, of course, but then there are all these current systems that are caused by our own magnetic field, the geomagnetic field, which is produced by the Dynamo Effect inside the Earth, in the liquid core of the Earth, but also by the solar wind, which compresses the magnetic field on the day side and stretches it enormously on the night side. And if you were in a spaceship away from the Earth, you would not see any of this. This is just an artist rendition of all these parts of the magnetosphere, but all these parts correspond to current patterns or current systems and magnetic field configuration. So that's if you ever study, and maybe you have studied space physics, then you would see this in detail. And the main thing that, and it's in red here, I want to mention it, the main thing that our magnetosphere is doing for us, and we don't think about it because we don't see it, but what it does is that it protects the Earth, not just the surface of the Earth, but our precious atmosphere. It protects that from direct impact with the solar wind. And the sun is not only radiating energy in the form of electromagnetic radiation, in the form of light. It's not only doing that, it's also producing a solar wind, which, if nothing stopped it, and if it could impact the atmosphere directly, it would erode the atmosphere very quickly. Well, on a geological time scale, it would erode it very quickly, and then we would be just a bare planet with no ocean, no free water, and very tenuous atmosphere, just like Mars. The next one is an illustration of this dynamo effect that I was talking about. The Earth, as you probably know, is made of a solid core at the center and a liquid core, and this is just metal that is liquid, in the liquid state, in the liquid core, and it's also metal here, but it has not condensated, but it has solidified in the solid core. And as time passes, the interior of the Earth is cooling down. It's cooling down at a very, very slow rate. It will take billions of years or hundreds of millions of years before it cools down to solidify the entire liquid core. So there would be very little liquid core or none at all. But meanwhile, the liquid core is sufficient to sustain this dynamo effect. There are some spiral-like convection patterns which somehow, and this is very complicated, some people are spending their career trying to model this and understand the phenomenon, and that creates the Earth magnetic field. I've asked one of my colleagues who does this kind of work at what rate the solid core grows. And he gave me the same answer that I had seen on the internet. It's on the order of 1 millimeter per year. So it doesn't grow very fast. It grows very slowly, in fact. But the thing is that considering that this liquid core is essential for producing the dynamo, as it grows, at some point there will be less and less distance between, or spacing between, the solid core and the boundary of the liquid core, and the dynamo effect is just going to dissipate. It's going to faint, to become weaker and weaker, and at that point, see what I showed you here, the protection that we have from the magnetosphere is going to weaken, and it's going to disappear completely at some point, or just about completely, and then we will have a difficult time, let's say, because we will be exposed directly to the solar wind. But again, this is not going to happen very soon. At 1 millimeter per second, we have another, if we calculate the time that it takes for this to solidify all the way to the edge of the liquid core, it would be something like maybe 1.7 or maybe 2 billion years. So that's a lot of time, but it's not enormous on a geological scale. Okay, measuring, now that I've given the broad introduction, and I've set up the scene for what I'm going to talk next, I'd like to introduce, or I was going to ask questions to the audience actually, but since it's not permitted to do that, for you to interrupt or speak during the presentation, I'll just continue, unless of course there's an exception, and then I can ask the question to the audience. But my question would be this: I mean, what I'm going to talk about is measuring the vacuum of space. In other words, measuring, there is vacuum in space, yes, but it's not pure vacuum. It's a very tenuous environment, very tenuous atmosphere or plasma, and it is made of particles, electrons, ions, and it's important to be able to measure these quantities, to measure the mass, the temperature, the flow velocity, the particle distribution function, etc. And I was just going to ask something very, very basic, a lot closer to our everyday experience. How do we measure the temperature in water and air, let's say? I don't know if anyone is allowed to to volunteer an answer. Let's start with the temperature. Does anybody would anybody like to turn on their mic and just give me a possible answer? It's very easy. I mean, it's not a trick. It's not a trick question. It's really easy.
Here
Okay,
we can make an exception. So anyone, if they want to answer, they can answer.
Yeah. How do you measure the temperature? It's easy. You probably have
Using a
something.
thermometer.
I beg your pardon?
Thermometer.
Could you? Yeah, that's right. Exactly. And this is how you can measure the temperature. And this thermometer, by the way, is not coming out of my freezer. It was just outside my window a few days ago. And one morning, and we've seen colder temperature or lower temperatures than that, but that morning I decided to take a picture to show the family. It does show -30, and it was -30. So I'm sure I hope it's not that cold where you live, but it can get quite cold in Edmonton in the winter. So that's for the temperature, and maybe I won't ask again, but what about the mass? How do we measure the mass of water or air? Water, well, it's easy. Okay, you can use just a scale. You put a scale. You have a beaker. You weigh the beaker first, and you put the water in. You measure the mass or the weight of the beaker with the water, and you can determine the mass per unit volume. So that's all right. What about air? Air is a little bit more tricky, but not that much more tricky. If you have a barometer, you can do this. You can measure the air pressure at a certain height when it's quiet, when there's no wind, very, very quiet column of air, and then you raise your barometer to measure the density or the mass of air per unit volume. But what about the plasma? How would you do this? A plasma is made of, well, it's a gas. A plasma is a gas. Although you can have a plasma in the form of a liquid too. You can say that a conductor is made of a plasma because it's made of free electrons. It doesn't have free positive charge, although there are carriers that are positive. So in that sense, a solid can also be considered to be a plasma or to have a plasma in it. But the type of plasmas that I'm interested in and that I will talk about in space, these plasmas are gases. They're made of free electrons and free positively charged ions that are very well described as an ideal gas. I'm sure everyone has seen what an ideal gas is in physics. This is one of the things that we see in thermodynamics and statistical mechanics. It's a bunch of particles. It's a gas made of particles that do not interact with one another. And the temperature is sufficiently high that we don't have to worry about quantum mechanical effects. So that's what an ideal gas basically is. So if we have these particles, then in order for this to be considered to be a plasma, the plasma has to be, or the medium has to be neutral, electrically neutral on a macroscopic scale, not on a microscopic scale, because if we go down to microscopic scales, then we start seeing individual particles, positive and negative, and clearly this positive charge here is not neutral, it's positive, but overall, if we look at a slightly larger scale, then the amount of positive and negative charges they cancel. The total charge very approximately cancel. So it's almost neutral. Okay, it looks very almost neutral. And also, plasmas can support collective phenomena. So, how do we measure the plasma temperature or density? Well, the answer is quite simple. We use any phenomenon that is affected by these variables. And I only mentioned density and temperature, but there are other properties as well. I mentioned previously the flow velocity. There is wind. There's the solar wind. I talked about that. But there are also winds, plasma winds or ionospheric winds in our near space environment, in the ionosphere and in the magnetosphere. So we can measure that by using a phenomenon which depends on these manifestations of plasmas, of plasma physics. And some of these phenomena that depend on the density or temperature are, for example, microwave interferometry. If we have a plasma in a region of space, and this is often used in lab plasmas. You have a blob of plasma, and then you propagate a wave inside the plasma, and you make it interfere with a wave which doesn't go through the plasma. So you bypass the plasma, you use a reflector, and you merge the two beams of radiation and make some interferometry. And the fact is that when a wave passes through a plasma, the wavelength changes, and therefore there will be a phase shift when you compare this wave that went through the plasma with the radiation that didn't go through the plasma. So that's one way. Thomson scattering is probably the best. Oh yeah, about microwave interferometry, it's relatively simple and it works well, except that it gives an integration of the density along a line of sight, and it doesn't give very good spatial resolution. It's possible to have spatial resolution if you do multiple lines of sight and then you do tomography, just like the X-ray tomography. Okay, so that's possible, but it's a little bit more involved. Thomson scattering is good because it provides spatial and temporal resolution. You just fire a powerful laser. The laser has to be fairly strong, and then you look at the scattered light at different points along the path of the laser beam. So that's one way of doing it. In space, one can use incoherent scattering radar. So that's the powerful radar. The radar at Arecibo was an incoherent scattering radar, for example. So it fires radiation in space, in the ionosphere, and the reflected radiation, it gives information on the density, temperature of the plasma, but the spatial resolution and the temporal resolution is not very good because they have to integrate the signal for minutes, I think, and the coverage is over maybe 100 kilometers or tens of kilometers, so they don't have very good spatial resolution. Faraday rotation is another one. So this is the property that light or radiation, which is linearly polarized, not circularly polarized, but linearly polarized. The plane of the linear polarization rotates; it changes as the light or the wave that we're using propagates in a medium. And it's interesting because I found out a while ago that somebody had proposed to use this phenomenon, Faraday rotation, to measure the current that that is associated with lightning on the CN Tower in Toronto. So the CN Tower, if you search on the internet, you'll see videos that the CN Tower is hit by lightning very well, not very often, but when there's a storm, because it's a high structure, and lightning sort of likes to hit the CN Tower, and by putting optical fiber around the CN Tower, and making use of the fact that some materials that are used to fabricate optical fiber have this property of supporting Faraday rotation, then, and of course the current that goes down in the CN Tower would induce a magnetic field in the optical fiber, and this would induce the Faraday rotation in the light that would be propagating in the optical fiber. But it was never done, unfortunately. But I think it's a neat idea, and maybe if you have something like this in your area, you might want to consider that. Current collected by a probe, and this is what I'm interested in, and I'll show you some of the work that we've done on this. This is probe, Langmuir probes, more specifically. So, well, I had prepared these pauses to ask the audience if they had questions. I'm not done, but maybe it's a good time to ask if anyone has questions or comments. I mean, you can make comments too. It doesn't have to be a question. I'll just wait 2 or 3 or 4 seconds and continue if nobody has questions or comments. Okay, continue. Okay, so now here's what we are doing, what we're working on. We are looking specifically, recently, we've been focusing on the physics of current collection by probes in plasma. Okay, so what is a probe? A probe, a Langmuir probe. So it's called Langmuir probe after Langmuir, who pioneered this topic 100 years ago. The papers that he was involved with date to they were written in 1926, I think, and maybe some a little bit later. But so it's almost 100 years old, this topic, and yet it's not all that well understood. And the estimates that people make with these probes are still very, very rough in some cases. I mean, the errors can be a factor 10. Okay, so what is it? It consists of a collector, a conductor, which can conduct electricity, and this conductor, it can be a sphere, it could be a cylinder, it could be a plate, a planar collector, and it is biased electrically, so there a voltage is applied to that object, and then it collects current. And from the current, from the relation between the current that it collects and the voltage that is applied, it is possible, by using theory and analytic expressions, it is possible to interpret these currents as a function of voltage, which are called a characteristic. So the characteristic is just the relation between the current collected and the voltage. So the characteristic can be used to infer, to determine the density, the temperature, and other quantities that I'm not going to go into. I'll just focus on the density and the temperature from analytic expressions. And one theoretical model that is used extensively in lab plasmas and in space is the orbital motion limited theory. And well, I didn't summarize what it is in this transparency, but I'll tell it in words. It consists of treating effectively particles as if there were no plasma. So particles are coming from one direction with a certain velocity, and for attractive potentials, they're deflected toward the collector, and their impact parameter, which I wrote as B here, their impact parameter is larger than the radius of the sphere, let's say, or the cylinder. And if the potential is repulsive, then the impact parameter is less than the radius of the sphere. And this is illustrated with this curve. And if you work out the mathematics around this, you find that these fairly complicated looking expressions for positive potential, for negative potentials, but really it's not that complicated. It's just a matter of integrating particle distribution functions and accounting for this dependence of the impact parameter on the voltage, and accounting for the fact that particles can be attracted to the collector or repelled by the collector. And the way to get an expression for the impact parameter is really very simple. You only need two laws of physics. You need conservation of energy and conservation of momentum. So by conservation of energy and momentum, you can determine the largest value of B, of the impact parameter, that will make a particle, just make it to be collected on the backside of the object, and you can find the largest B that will allow a particle which is repelled by the collector to be just grazing the surface of the collector. So that's, and you can try that on your own if you haven't done it already. And once you've done this and you assume a Maxwellian, I guess Maxwellians are very, very well known, a normal distribution for the velocity distribution of plasmas, of particles, then you get these intimidating expressions, but they're not that bad. Okay, so what about the floating potential and the bi-shielding? That's another thing that's quite important, and I'm going to actually draw in person here. I'll illustrate something with my tablet. So suppose that we have a plasma. Let's say we have a plasma with positive, negative, positive, negative, positive, negative. I'm not going to draw too many of these. So the negative, of course, are the electrons. The positive are the ions. So the question is, which of these? So let's say that. Let's be specific. So this is H plus, and these are electrons. Okay. The question is, which of these are the fastest particles? Now, I would appreciate it if someone could volunteer an answer. So the fastest particles, which one are they? The H plus or the electrons? Well, let's put a question mark here. If no one volunteers an answer, then I will tell you. Okay, I'll tell you. It's the electrons. So the electrons. I hope you can forgive my handwriting. So these are the electrons. And why? It's because at equilibrium, the electron gas and the H plus, the proton gas, will have the same temperature. So TE is equal to T, let's say I for ions, and let's just say that it's equal to T. And the average energy per particle is equal to 3/2, for an ideal gas, 3/2 kT. Okay. And T is the same for both electrons and ions, and this is the average energy. There's only one kind of energy here if these particles are free, and I didn't prove that, but the interparticle energy of these particles in the electrons and protons in a plasma, the interparticle energy, potential energy, is small compared with the kinetic energy. So that's 1/2, of course, mv squared. So if I have if I look at the average energy of the ions or the electrons, I have I here or E there, and of course I have I there and E here, there. So if the energy is the same, it's the same because they have the same temperature. And the masses are very different because electrons are much lighter than protons. Then the velocity has to be much larger for the electrons than for the ions. Okay. And what's the consequence of this? Suppose that initially we have Q is equal to 0 in here. So there's no charge on this object, and it's neutral. What will happen if I introduce this object in a plasma where I have very fast electrons and very slow protons moving around? Well, what will happen is that the electrons will randomly, due to thermal motion, random motion, they will hit the surface of the object much more than the ions. So the ions will also hit the surface of the object, but much more slowly, okay, because they have a much smaller velocity. And as a result of this object is going to become charged negatively. So we will have an accumulation of negative charges on the, I won't draw it all around the circle, and then the charge is no longer going to be equal to 0, but it's going to become less than 0. So it will become negative, and the plasma surrounding the object will try to cancel the when this is I'm speaking in familiar terms here. It will tend to cancel the charge, a negative charge, and there will be an accumulation of positive charges. And these negative, that's the thing, these negative charges, as this object gets charged, they will start repelling the electrons until such time as the flux of electrons to the object is equal to the flux of ions to the object. So this this moment when the flux of all the species, the negative particles and the positive particles, is equal to 0, this will correspond to a floating potential. So let's call it FVF. So it's like floating a boat on a river. We take the object, we immerse it in a plasma, and after a while it just sits there, and there's no net current being deposited on the object. There's as many electrons per second as there are ions because of the charge that the object has acquired because of this bombardment by the other by the plasma particles. Okay, this is just one process. There are many more, but I don't want to spend too much time on this. Okay, so and what about Debye shielding? Well, the Debye shielding is um, is is a process by which if you put an object with a certain charge in a plasma, after a certain distance, the plasma will have shielded effectively this charge, and the distance or the scale length over which this shielding will take place is called the Debye length. So I'll try to write it nicely. The Debye length. And the Debye length, you can derive that, and again, maybe I'm telling you things that you already know, but the Debye length is given. So let's say just for the electrons, let's ignore the contribution for the ions. It's epsilon 0 kT over n, the density of particles e square, and all that to the square root. Okay, so that's the Debye length. So you see that the Debye length increases with the temperature and it decreases with density. So in a very hot plasma, the Debye length is large because there's a lot of thermal motion, and in a dense plasma it's small because there are lots and lots of particles to contribute to this shielding. Okay. Now, how do we do this? What we want to do is find ways to interpret probe measurements, but well, we know that there are ways because pretty much everybody doing an experiment in the lab or in space is using this OML, this orbital motion limited theory that I briefly described a few minutes ago, and it's well known that the estimates made with this theory are sometimes very, very approximate and off by up to a factor 9 or 10. I mean, there has been cases where it's documented that the density is completely wrong. But still, people continue to use these because it offers a convenient and very fast way to infer physical parameters from characteristics, from probe characteristics. Remember, a characteristic is the relation between the collected current and the voltage. Yeah, so how do we do this? How can we do this? We can do more sophisticated theories, and people have done that. But the thing is that you cannot, it's not possible to account for the most important physical processes and the geometry, because the geometry is important in this case. With theory typically assumes that you have a single probe isolated in space, that it doesn't interact with anything nearby. There's no satellite around, no vacuum vessel, no other instruments. So there are very stringent assumptions made in developing a theory. They're useful, and they give convenient analytic expressions that can be used very, very quickly. And that's the reason why they're used, why they're so popular. It's because they're relatively simple, these analytic expressions that follow from theory, and they can be used quickly, very fast. So you do an experiment, you don't want to wait a week before you interpret your probe measurement in terms of density and temperature. You'd like to do it in real time. So that's possible to do. It's possible to do this with theory, with analytic expressions, but not, let's say, with computational techniques. So with computational techniques, it is possible. However, given densities and temperatures and magnetic field and ion composition and flow velocity, given all these parameters, it's possible, relatively straightforward, in fact, to calculate probe currents as a function of voltage, probe characteristics. But if one is going to do a computation or computational study and try to simulate a probe characteristic, just one simulation, just a single simulation, could take several weeks. So you cannot. It's just not practical to use these direct simulations in order to interpret probe measurements. However, now we hear a lot about artificial intelligence and machine learning and things. One very basic application of machine learning is multivariate regression. And this can actually be used to take a number of simulations, which covers a certain region of parameter space, and infer physical parameters from calculated currents. So in other words, we're mimicking. It's a matter of reproducing on a computer what happens in real life. Instead of doing the experiment, we just take a computer model, a sophisticated computer model, and calculate the density, the currents rather, that a probe or a collecting device would measure given certain conditions and given certain voltages. And we construct a data set. It's a synthetic data set, and this is why it's in red. It's very important. It's a synthetic data set. And then with this synthetic data set, it is possible to train models using machine learning techniques, in particular regression. And this would work, and it does work, very fast, and it can be used to actually interpret probe measurements. But to my knowledge, nobody uses that yet. And that's what we're trying to promote. We're trying to sell the idea that this technique is useful, it works, and that it should be used. But it's not trivial to do, because we do need this synthetic data set. So that part here is very important, this synthetic data set. So how does it work? There are multiple methods for doing regression, and the one that we've tried two actually. We're trying radial basis function regression, and we also looked at neural network, deep learning neural network. But I'll talk mostly about a radial basis function. So this is the simplest one. It's the simplest regression technique that I know. It consists of training a model, a regression model, with a number of data, of training data set. We need a training data set in which we know the independent variable x, and we need to know the dependent variables. So in this case, the independent variables would be the currents, okay? Because what we want in the end, we want to be able to take a characteristic, we want to be able to take currents and infer parameters such as the density or the temperature or the flow velocity. So we in this training data set, we have a large number of currents or characteristics, and we know, because we've done the simulation. So in the simulation, we know which density, temperature, flow velocity, etc. that we've used. So we know these, and then we can train a model given this knowledge. And this is just an illustration of how it works. Suppose that we have a number of reference points, and the choice of these reference points is critical. It's very important to choose the reference points correctly and optimally. So once we've decided which reference points or pivots, we call them pivots, we're going to use the regression the regression consists of doing some kind of linear superposition of functions of the distance between the pivot points and the point where we want to infer variables. So here we would have a characteristic and a density, temperature, another characteristic, density, temperature, etc. So those would have been calculated with kinetic simulations in 3 dimensions, So we would know all these points. We would know these data entries, and we go to the lab or to space, and we make a measurement. We measure X. We don't know what Y is. We just measure X, and we apply this expression here with the pivots that we have selected, and this will give us the value or an estimate of the value of Y. Here. We measure X, we infer Y. This is nothing else but than interpolation. You could think of this in terms of a one-dimensional independent variable and a one-dimensional dependent variable. It's just a Y as a function of X, and the interpolation is done in terms of distances from various pivots to the point where we want to infer the quantity. And in a case, the characteristic was determined from 4 currents, but it doesn't matter. It could be much more than that. In fact, I show you an example where the characteristic is characterized in terms of 25 currents and 25 voltages. And this is it right there. This work was done with a summer student, Jonathan Chalatornik, and it was published in Frontiers in Physics 2 years ago, and it consists of just establishing whether or not this method works. So in order to assess the feasibility of the method, we needed a large data set. And we didn't want to do hundreds and hundreds of simulations because that would have taken years to do all these simulations. So we just used the OML theory that I mentioned previously was not all that accurate, but nonetheless, for the purpose of assessing the applicability of the method, it's sufficient. So we used OML and we generated a lot of characteristics and for a lot of density. So that this is the density, temperature, and this corresponds roughly to the ionosphere. We sampled the ionosphere using a model called the IRI model, the International Reference Ionosphere. If you search that online, you'll see that you can access a website where you can actually calculate, you can apply this model to determine the density and a number of things in the ionosphere in any region of the globe, of the planet, and for various times as well. So it's something to play with if you're interested in this topic. So anyway, so we generated all this big data set using the OML theory. So it's very quick, it's very fast to calculate the characteristics with the OML theory for various plasma conditions as prescribed or as obtained from the IRI, the International Reference Ionosphere model. And then we trained the model, an RBF model, with I think it was with five pivots. So with only 5 pivots, we were able to do an excellent representation of all the densities in here. And this is the correlation plot. So this is the model prediction, our radial basis function prediction of the density. And this is the actual density used in the in our synthetic data set, and the correlation is excellent. I don't have a correlation factor here, but it must be at least 0.99, maybe another 9. I don't know. And in this case, the characteristics were represented, they were discretized in terms of 25 currents for 25 voltages ranging from -5 volts to +5 volts. Maybe this is too technical. I apologize for this these technical aspects, but this is almost artistic. I like these pictures. This shows the position in this parameter space. You see in this space here, the NT space. I'll show you the pivots in a moment. So the pivots were here. There's one here, which is not very visible. another one. So we have 5 altogether, 5 pivots. And with only 5 pivots at these strategic locations, and I'm not going to go into the choice of these locations, but I can talk about it if there are questions at the end. And these colors refer to the relative error in the predictions of the density. So the largest relative error are of order 1.4%, and they occur in this region, right in more or less in between this extreme here and all the other points that are located there. That's for the density, and for the temperature we have a similar plot. And here the errors are, well, these are the absolute errors. But so that a relative error of 1.4% is really very good. But of course, this is done with synthetic data. It's not done with real data. Another thing, that this is a completely different project, and this student, Akinula Oluwokere, is doing his PhD now at the University of Alberta, and one of the things that he's worked on, and he continues to look at improvements and extensions of this work, is to design an apparatus to determine the floating potential of a satellite in space. I did say previously, if you remember, this blue circle in which I wrote negative signs and positive signs for positive charge and negative charges around the blue circle. This blue circle, when it becomes negatively charged, it acquires a negative potential in space with respect to the background plasma. Well, it's the same thing for a satellite. The satellite is just like the blue circle. If you immerse it in a plasma, electrons will precipitate a lot faster initially than ions. It will become negatively charged, and as it gets negatively charged, it will start repelling the electrons and attracting the ions, and eventually there will be no net current going to the object, and it will have reached its floating potential. And it is important to know the floating potential of a satellite because it affects a number of measurements. And the technique that the student has or is working on, and this has been, it's not yet accessible in the regular issue of IEEE Transactions on Plasma Science, but it is accessible as an early access paper. It was accepted just recently. So here's how it works. We use the OML approximation, and we have 2 probes, and these probes are fixed bias probes. So the bias, the voltage of that probe with respect to the satellite is constant in time, and likewise with this one, but they're different. And by looking at the differences in currents that are collected by these probes, it is possible to determine the floating potential. And I'll show you how this works. So this is a result of or an illustration of the simulation results that Akinula obtained for one of these probes. So the probe consists of a sphere of radius 4 millimeters, and there's a post holding it. The post is biased to the same voltage as the sphere, and here's the profile, a cross section of the this is the charge density, and this is the density. This is just the ion density, and we see a big wake behind the probe because plasma is coming at a supersonic speed. I mean, this is coming at satellite orbital speed, basically, approximately 7,500 meters per second. So this creates a wake behind the sphere, and we can see the signature of the wake in the charge density here. So here, in the OML theory, one would assume that the sphere is isolated in space, so there's no post. that there is no flow, and then there is flow, of course, because we see this big wake, and this OML is just not applicable in this case, although it can be a useful approximation. So here's the first approach that Akinola followed. He used the OML expression. In the equations that I showed previously, there were these error functions and exponentials. It was very complicated. But if we assume that the voltage with respect to the background plasma, the floating potential plus the bias voltage, let's go back up. This is the floating potential of the spacecraft with respect to the background plasma, and this is the bias voltage. It's the voltage of this probe with respect to the spacecraft. So the voltage of this tip here of this probe with respect to the background plasma is just VF plus VB1, and likewise for VB2. So if this quantity here, which is the voltage of the probe with respect to the background plasma, is larger than the temperature in electron volt, then this is a very good approximation of these very complicated expressions that I showed you previously. And if we use that now for the two probes that I illustrated in the previous slide, so I write I1 is equal to this, and A is just the same multiplicative factor. It involves this NE, R square, etc. So it's just a multiplicative factor. Then it is possible to solve for the floating potential plus the temperature in electron volt. This here is amounts to the temperature in electron volts. And what we find is that the floating potential is equal to this simple expression, relatively simple expression, just a ratio of two quantities that are, everything is known here. We know the bias voltage and we know the current because those are measured, minus the temperature. But, and here you have to know about the ionosphere. The temperature in the ionosphere is typically significantly less than the floating potential of a satellite. The floating potential of a satellite is, at least for low Earth orbit satellites, is of order -2 or -2, -3 volts. And the temperature in electron volts, well, it can range from not minus, the temperature is not negative. It can range from 0.05 to 0.3 electron volts. So this is small compared to the floating potential for a satellite. So as a first approximation, we can just say that the floating potential of a satellite is given by this expression, where everything now is measured and known. And I'll show you results in a moment, but I just want to briefly describe the other two approaches that he followed. The other attempt that Akinola made is to predict the floating potential directly from radial basis function regression. So the same expression that I showed previously, so it's just an interpolation in a multi-dimensional space. And in this case, the multi-dimensional space X is made of tuples of current, so I1 and I2. So this X is a two-dimensional expression, and those are the components are I1 and I2 corresponding to the two probes. So that's how the model was assumed to be used for interpolation, and so that's the second approach. The third approach consists of using this expression, which is the analytic approach based on the orbital motion limited theory, and correct any error, so that there will be a discrepancy between this and the actual values from the training data set, and correct the error with regression, with RBF regression. Okay. So now let's see how these things perform. So here's the purely analytic expression based on the OML theory exclusively, we see that it's not so bad. When we looked at the current profile collected by the probe and the post, we saw that it was not perfectly symmetric around the sphere, and there was this big wake, so the assumptions made in the OML theory are not perfectly well satisfied, but nonetheless, OML is performing rather well. Okay, now we try RBF only without OML, and we find well, the maximum error is about 1, maximum absolute error is 1, and here it was 0.8. So we can say that it's comparable, although this one looks a lot better than that one. And finally, if we combine the two approaches, so we look at this one, and then we use RBF regression method to correct the discrepancy between the analytically predicted floating potential and the actual floating potential, then we obtain a much better fit. So that was contained in his paper, and he's pursuing this with other things than just the floating potential. And in this paper, the referee asked us to find a way to verify this experimentally. Initially, we hadn't thought about that, and we didn't think it was particularly relevant, but actually it was a good suggestion, because we came up with something which I think is interesting and hopefully will be implemented at some point in a space mission or perhaps in the lab. And here's how it goes, very quickly. We have the satellite with a floating potential. If we have a 2-probe unit here and another one, we can bias this unit to a certain voltage V1, bias this one with a certain voltage V2, and here we met using the technique that I just discussed. We can measure the floating potential of that unit. We can measure the floating potential of that unit here, but the floating potential of this unit is, I mean, if all works well, it should be the floating potential of the satellite plus V1, and here the floating potential of that unit should be the floating potential plus V2, and therefore, if I subtract these two voltages, I should find that VF1 minus VF2 is equal to V1 minus V2, which are known. Okay, everything is known here. So that's one way of testing it. And the interesting thing is that this concept of using 2 units like this to measure the floating potential does not have to be with the 2-probe system that we are proposing. You can put any instrument here that can be used to measure the floating potential and just make a comparison between these two measurements of the potential. Okay, another project that a student is working on is, I'm sorry I couldn't get a picture of Akinola, but Guangdong was generous enough. He sent me a picture. It's a flow meter. How am I doing with time? Am I exceeding the time by a lot? Because I can. Well, I don't have much more to say. So Guangdong is a PhD candidate now at the University of Alberta, and he's assessing the feasibility of using this very simple device to measure the flow velocity of a plasma, the transverse flow of a plasma. So the main flow is from the ram direction. The ram direction is the direction in which the satellite is traveling. So that's the ram direction. But there are also transverse flows, and there are a number of devices that have been proposed to measure these transverse flows as well as the ram flow. And this one is particularly simple, and it should be rather robust, because the more sophisticated you make your instrument, the more likely it is to fail. And there's a good example of this. I don't want to insist too much on that because it's somewhat unfortunate. but I'll mention it briefly in a moment. So by collecting current on all these segments, as well as on the top ring, it is possible to assess the density of the plasma and the flow velocity. And this instrument has a six-fold rotational symmetry, and it also has mirror symmetry. Suppose that I simulate flow going only in sector 7. Let's say that I have a big data set for flow in sector 7. I can extend this to flows in sector 8, because all I have to do, well, one thing to notice is that when I simulate this flow in sector 7, of course I measure the current in sector 7, 1, 8, etc., in all the sectors. So if I have a data set for flows directed in sector 7, I can extend this to flows in sector 8 simply by taking the mirror image in this line here. So I can take mirror images from here to there, from here to there, etc. And then when I do this, I have to do the mirror image of all the other sectors, of course. And then I have a database that covers 7 and 8. And once I have a database for 7 and 8, I can just rotate because there's rotational symmetry. There's this six-fold rotational symmetry. I can take all these values of the current obtained for different flows in these two sectors and rotate it. And of course, as I do this, I have to rotate the currents in all the other sectors as I rotate from 7 to 8 to 9 and 10, etc. I hope that this is clear, but that's what he's working on. And in fact, he submitted a paper recently which came back from the referees with relatively favorable comments, but we still have to do some work on it. And Guangdong likes to try things, so he tried RBF. So he did try RBF, but he also tried neural networks. And he found that for this method, the two methods are, or for this problem, I should say, the two methods are more or less equivalent. And in some cases, RBF is a little bit better. In other cases, neural networks are a little bit better. But the disadvantage of neural networks for a problem like this is that it takes a lot of data to train a model, while with RBF, it's possible to train a model with relatively small data sets. And here's an illustration of the simulation results that he obtained. This is for plasma flow directly from the RAM direction. So in here, the distribution of current on the bottom plate would be uniform, and this shows what the distribution is when there's a side wind, when there's a transverse flow. The flow is in this general direction here. Yes, I have the hand here. So the flow is in this general direction, and by measuring or using the different currents in these sectors, and the Guangdong did not illustrate the outer sectors, but there are outer sectors here. Then by measuring or by using the measured currents in all these sectors, it is possible to assess the flow velocity relatively accurately. And this is an example of what he obtained. He compares actual flow velocities from his database with inferred velocities from the from RBF, I think it is in this case. Yes, it is for RBF with only 5 pivots. And in order to see how robust this inference method is, he introduced some noise in the measurements of the current. So he introduced 2% of noise, and of course the skill of the predictions decrease. It's not as good, but it's still reasonably close to the data from our data set. He also used that to infer the density, and he's getting 27% maximum relative error, but 7.4% in the root mean square relative error. So if the relative error, root mean square, is relatively small, the maximum relative error is a bit larger, of course. But that's not terrible, because it's not as bad as one might think, because a lot of techniques used to infer the density produce uncertainties that are much larger than this. Another project that a former student of mine did is with SWARM, the SWARM satellite. And SWARM is an ESA mission, and the main goal of the SWARM mission was to map and measure the Earth magnetic field with unprecedented accuracy. Unfortunately, there were a number of technical problems with SWARM, and it has to do mainly with this object here, the front plate, and the ion imagers. The ion imagers were intended, and actually they do work, they do work, but they were intended to measure the transverse flow velocity. There's a microchannel plate with lots of small detectors in each of these two shells that we can barely see here, and they, by looking at the distribution of precipitating ions on this microchannel plate, it was possible. It should have been possible to infer transverse velocities with pretty good accuracy. Unfortunately, these satellites, there are three of them. There's one here, one there, and one that is barely visible up there. Unfortunately, these satellites were stored in Russia in a not a shed, but in a, how do you call it? In a place where they store satellites to be launched, and it was scheduled to be launched at a certain date, but it was launched actually at a much later date. And during that time, I think that's the explanation anyway. I think that these sensors were contaminated by humidity in the storage room, and that would explain why they're not functioning quite as they should. Every once in a while, they have to clean them, to heat them, to get rid of contaminants. But that's not what I want to talk about. And this plate here, the front plate, is used as sometimes when the imagers are not used, the front plate is used as a large planar Langmuir probe, and Pedro did some work about this, but I'm not going to discuss it now. What I want to talk about is the recent work that he did with the two Langmuir probes under the satellite, and I can see them because I know where they are. But there's one here, and there's another one there. They're really, really small. They're very tiny Langmuir probes, and they are spherical Langmuir probes supported by a post, which is about 10 centimeters long. This whole satellite is approximately 10 meters long, and we have simulated the whole satellite at times, but mostly for the study that the recent study that Pedro did, it was just a truncated part of the satellite that was considered. So here's an illustration of the geometry that we used. We accounted for the front plate, for the shells in which the imagers, the ion imagers, are located, and this shows a bigger illustration of the probes. So we have the support here, and the distance between the base of the satellite and the probe is approximately 10 centimeters. And let me just say one thing that I forgot. It looks like this satellite should be propagating toward this direction, right? So it looks like this should be the RAM direction, but actually that's not the case. The RAM direction is this direction. The satellite is propagating toward the left on this illustration, not toward the right. But we don't have to worry too much about aerodynamics in space because the atmosphere or the plasma is so tenuous. Okay, and here are some very basic simulation results. Pedro illustrates, he did this in his thesis and also in the paper, he's illustrating the trajectory of particles toward the probe, but assuming conditions that match the OML assumptions. In other words, he's considering an isolated probe in space, and he ignores magnetic fields, the presence of a satellite, the presence of the post. Everything is ignored except the probe, the sphere of that the probe is made of. And he's showing, and that's kind of obvious, he's showing that for light particles, let's say for H plus ions, they are deflected significantly more than for O plus ions, which are somewhat heavier. And therefore, these H plus ions have a larger impact parameter. You remember this B parameter that I showed previously when I talked about, or when I introduced the OML approximation. So the impact parameter is much larger for lighter ions than for heavier ions, and therefore it is important to account for these lighter ions in space. And the reason I mentioned this is that the analysis of the data obtained from these Langmuir probes ignores that. It assumes, well, initially at least, until we did the work, it assumed that everything was pure oxygen, and it led to significant it's overestimate, yes, of the density. The density was overestimated considerably because with only oxygen ions, we should have a smaller impact parameter, but in reality, there was a lot more ions hitting the probe than expected because of this minority H plus ion species. And the relative importance of H plus to O plus is significantly more than their relative concentration. So H plus could be 5% and O minus 95%. There are other species, but I'm simplifying things here. But their effect will be much more than 5%. So here's the consequence. Remember what we had previously. Whoops, here it is. The particles were going like this and like that. It was symmetrical, up and down. But once we put the geometry, we have something completely different. This is negatively, well, it's not biased because it's floating. So that this has a negative floating potential, and it attracts ions, and it attracts light ions a lot more than the heavier ions. But the net effect is that we get a lot less ion current on these probes than we would if the probe were isolated as assumed in the orbital motion limited theory. So theory is useful, but sometimes it has to be corrected or improved with more powerful means, such as computer simulations. And in his work, Pedro came up with an analytic expression. I won't show it, but this is going to be published very, very soon in JGR, Journal of Geophysical Research. In summary, analytic approximations can be useful, but we have to go beyond them if we want to get accurate estimates. the analytic expressions are used because they're simple and they allow fast inference of measurements, and that's good. I mean, if I were doing an experiment, I would probably use analytic expressions initially, but if the experiment relies heavily, and if the measurement of density is important, then I would spend time doing some simulations and constructing a synthetic data set that I would then use to infer useful parameters from my measurements. The analytic expressions, as I mentioned previously, cannot account for all the physical effects that are important and the geometric conditions under which measurements are made. And the response, the best way to really quantify the response of instruments is to do simulations or to do measurements. But the problem is when you do measurements that you never measure the density directly. It's not like taking a scale and pouring water in a beaker, in a graduated beaker, and then putting it on the scale. It's not that simple. What you measure in space are not densities. You measure currents. You measure phase shifts. You measure resonance frequencies. You measure a number of things, and those measurements have to be interpreted in terms of temperature and measurement. So it's very tricky to use measurements to calibrate an inference algorithm. One needs at least two measurements, two independent measurements in order to calibrate things. Are there questions? I guess I should probably stop, but I have a few more slides that I can show. Just let me know, please. Should I stop now or?
Sir, it's fine if you continue.
Okay. All right. So now I talked about the natural environment of space, of near Earth space, and let's talk about the anthropocentric or anthropogenic environment. And there are lots of nasty things in space. There are high energy particles, cosmic rays that have fantastic energies, coronal mass ejections, and all sorts of things. But since the beginning of the space age, many satellites have been put in orbit. A lot of them in low Earth orbit. So there's a special name for these satellites. They're called low Earth orbit satellites, and there's an acronym of LEO orbits, and there are some scattered pretty much around the Earth, and a lot of them are located also at geosynchronous or distances. So that those are the ring here. We can see that a ring. This is for geosynchronous satellites. This is where they are. And it's not just satellites that are functional that are there, but there are also, and also this is surprising. I didn't expect that when I first looked into this. But when satellites or rockets are sent in space, sometimes the battery explodes, and that causes debris, and sometimes the fuel tank explodes. So now there are measures that agencies, national agencies follow in order to minimize this risk, this hazard caused by debris. And one of these measures is that once a satellite, especially in geosynchronous orbit, because those satellites are really far from Earth, there's very little gas there, and very little plasma, so they can orbit almost, well, not indefinitely, but they can orbit for a long time before they're slowed down by the solar wind or by the solar radiation. Solar radiation is actually responsible for deorbiting satellites, small satellites, but it takes a long time for this to happen. Anyway, so one measure is to take these satellites in geosynchronous orbit and put them in so-called graveyard orbit. So the graveyard orbit is 300 kilometers outward, away from, well, not inward, but outward, away from the geosynchronous orbit. And another one is to empty fuel tanks, just empty fuel tanks so that they don't explode. Once a rocket has released its payload, or once a satellite has ended its mission, just empty the fuel tank just to make sure that there won't be any explosion. And it looks very crowded, and one might think, wow, how can you do this? How can you put anything in space with all this clutter of satellites and pieces of debris? Well, space is big, and the mean distance between satellites is in the tens or usually hundreds of kilometers. But the problem is that these satellites are not sitting still in space. They're orbiting, they're traveling at high speed. And it does happen occasionally that satellites collide with other satellites or with other pieces of debris, and then it causes more debris. And this led Donald Kessler in the 1970s, late 1970s, to formulate this Kessler syndrome, whereby debris would hit debris and produce more debris, and at some point it would become practically impossible to go to space. Because of that, any spaceship would be damaged by pieces of debris flying in space. It doesn't seem to be a problem yet, but it could if one is not careful. And here's another interesting plot, and I'm almost finished. It is a plot showing the distribution of debris in space as a function of time. And if we look at the ordinate, it's an impressive number. It's not 1,000, it's 20,000. So here we have 20,000 pieces of debris, and in fact there's a lot more than that, because this is debris of a certain size. I forgot what, maybe 10 centimeters or more. But if you go down to the centimeter or a little bit below, then it's millions of pieces of debris that are orbiting the Earth. But fortunately, very small pieces of debris tend to deorbit fairly quickly due to, in particular, air drag, if they're not too high in altitude, and radiation pressure from the sun. So the light exerts pressure on a piece of debris, and if maybe I can illustrate this with a very very quick illustration. So let's take this. Okay, so this is the Earth, and the sun is here. So the sun is radiating in this direction. If we have an object that's going in this direction, it will feel radiation pressure, but the pressure is going to be higher going this way than going that way, because here there will be a Doppler shift in the radiation. There will be a blue shift of the radiation. I mean, it's very small, very, very small, but it exists, and it's always occurring. So here the pressure will be higher. It will tend to slow it down, and the pressure will be a little bit lower, but it will speed it up. But it will speed it up less than the slowing down that occurred on the other side. And the net effect of this is that small pieces of debris lose angular momentum, and eventually they just burn in the atmosphere. But it could take a lot of time for that to happen. Nonetheless, if these pieces are far away from the Earth. Let's see if I... Okay, so another thing is this is just statistics, and you can go to this website and find that yourself. It's amazing. 100. Let's look at the the bottom one. 128 million objects from that range in size from 1 millimeter to 1 centimeter. And an object of 1 millimeter, I mean, it looks like a small thing, but if it comes at you at a few kilometers per second, it can cause some damage. So it's something to worry about. And big satellites such as the weather satellites, remote sensing satellites, and the International Space Station periodically, frequently have to adjust their orbit in order to avoid debris, to avoid collisions with debris. And mitigation, I already mentioned that. So thank you. And if you have questions, I would be happy to try to answer them. I can't promise that I have answers for all your questions.
Okay, sir, we will start with the Q&A section. So one of the questions that we've received is, why would the transverse flow velocity be different than the ram speed flow, since the situation seems symmetric for the plasma in space?
Yeah, well, it looks symmetric, but it's not. There is space weather. There are winds occurring in the ionosphere and in the magnetosphere. There are all sorts of current systems and plasma flow systems, so that the plasma in space is not just quiet. It responds to changes in the magnetic field configuration. It responds to the to the solar wind, because the solar wind can compress. I should say that the solar wind velocity can range from maybe 200 kilometers per second up to, maybe I did say that, to 900 kilometers per second, almost 1,000 kilometers per second. And these changes in the solar wind velocity can occur very abruptly. They can be very, very sudden. And then the magnetosphere starts to shake. I mean, it starts to ring if like a bell if it's hit by a shock front from the solar wind, and that causes flow velocities close to the Earth. The plasma is more or less, not exactly, but more or less co-rotating with the rotation of the Earth. Okay, it's rotating with the Earth, more or less, but there are deviations from that, and the side wind, even though the satellite is going around the Earth with a certain ram velocity in a certain direction, there are variations in the magnitude of the ram velocity wind, the wind that's coming directly at the satellite, and there are also variations, fluctuations in wind or plasma wind transverse to the direction of propagation of the satellite. I don't think I have answered the question because I didn't tell you why. Well, sort of. It has to do with space weather and magnetospheric activity.
Okay, sir. Next question. In slide 37, you've shown that why are ion trajectories deflected near the front plate?
Why they are deflected differently? Because they're all coming. Okay, they're all coming at the same speed, but they don't have the same energy. The lighter ions, the H+ ions, have less energy. They can be deflected more than the how can I say? Imagine that you have somebody. I'm trying to think of an example that we could relate to in everyday life. Suppose that you have a bicycle. Okay, you have someone goes by you with a bicycle, and if you push on the bicycle, assuming, I mean, don't push too hard because the person might fall, but if you push on the bicycle, you can force the rider to steer the bicycle by a certain angle, let's say. So you just push on the bicycle will change direction. But if a car comes by you, if it's a car, you can push on it, but it's not going to change direction very easily. Okay? You have to push really hard to change its direction. It's the same thing here. We have light particles that come by this object, and in fact, this object, these are positively charged particles. So this object would be, they would be negative. So it would be negative, right? The potential would be negative, and it's attracting these particles that are passing by, and the hydrogen ions that are very light, they will feel this attraction. They will respond more quickly or more strongly to this attractive potential than the heavy, the truck. Think of this as a truck coming. I mean, it's not going to be deflected very much, but this is the bicycle, and it will be attracted more than by the attractive potential. Does that answer? Is this okay? Any more questions?
Yes, sir. Okay, another question. Slide 35. Can you please tell the challenges and elaborate on a little about the curved equipotentials in and around the front plate and the Langmuir probe of the swarm?
Did you say 35?
Yes, sir.
I think I missed part of the question because there was some interruption in the sound. What was the question? Could you repeat it, please?
Okay, sir, I'll speak again. Yes, sir. Can you please tell the challenges and elaborate upon a little about curved equipotentials in around the front?
The equipotentials, but I don't think I'm showing any equipotential here, or am I? Can you share the chat with me?
Okay, sir, I'll type it out.
There. How can I see the chat?
You can see that on the top right corner, you can see a
Oh, yes.
and
I got it. Yes. Right. Oh, okay, yes. No, I'm not seeing any question there.
I think she's typing it out. Once she's done with it,
Okay,
she'll.
okay. Can you please tell us about the challenges and elaborate upon a little about the curved equipotentials in and around the front plate and the Langmuir probe on swarm? I don't know if slide 9 or 35 is the best one for that. Maybe, oops. Well, this one, actually, I do have an illustration of that in a paper, but unfortunately, I don't have it with me. But I'll try to illustrate it with my pen. Okay, so but it's going to be very rough. So I'll draw the ram face. So the ram face is like this, and we would have the front plate would be like that, and we would have these shells here, and then the Langmuir probe would be here, and with use the freehand drawing, we would have a sphere here, and we have these shells here, right? There are some shells here, and there's another one like that. So the equipotential, you want to know about the equipotentials, right? Well, that's what I remember from this equipotential. Yeah, okay. So the equipotentials, by memory, this is biased to negative 2. Well, it's not biased. It's just a floating potential. It's negative 2 volts, and the front plate is biased to negative. So V B is equal to negative. Oh, I didn't give myself enough room. Let's move this over there. Like that. It's negative 3.5, 3.5, and this is what is used in the experimentally on swarm when this plate is used as a Langmuir probe, and this is also biased to 3.5. So V B is equal to negative 3.5, so that the potential of the sphere with respect to the background plasma is negative 5.5. So the equipotentials now, I can't draw them exactly, but they're sort of like that, and like this, and here we would have closed equipotentials because the potential is more negative, very close to the sphere than elsewhere, and here as well we would have something like this. Well, okay, I don't know if that answers. I mean, if you want, I can go back to the paper and show you a plot for the equipotentials. I don't mind doing this. It shouldn't take too long to do. Do you want me to do this? Hello?
So I think we'll get back to you on that. The person who has asked the question, if they want it, we'll let you know later. So I think we'll move on to the next question now. Will that be fine?
Yes.
So, there are questions in the chat box, and Sandra will also be reading it out.
Okay, there's a question from. I hope my voice is audible. There's a
very audible.
Okay, thank you. There's a question from YouTube. It's asked, can plasma state be attained physically?
Can plasma state be attained physically? I'm not sure I understand, but of course it exists. It can be created. Plasma nowadays are used for all sorts of things. They have been used for surface treatment for many years, and now more and more they're used in medicine. And then people are working with room temperature and atmospheric pressure plasma to treat infections, let's say, and to heal certain wounds. So that this is plasma is still a very active area of research, and it is important in space. It's important in engineering, in material properties, and now in medicine. So yes, it can be created in the lab, and it can be used for very practical applications. Let me know if I don't answer your question.
The next question from YouTube. Have you been able to generate the number density profile of particles along the orbit of a satellite?
Along the orbit, along what?
Along the orbit of the satellite.
No. And the reason is that we haven't constructed a data set yet for swarm. Of course, the swarm data analysis team, they have produced densities along the trajectory of swarm. They do it routinely. This is a data product that they produce, and it's available on their website. However, they still use the OML approximation. They still use assumptions about the distribution of masses, the certain fraction of oxygen, hydrogen, and other species. And their estimates are improving. Initially, they were assuming pure hydrogen, and it was giving them very inaccurate results, and they knew that. Now their estimates are getting better, but there's still room for improvement. But unfortunately, we haven't reached the point where we can apply our method to swarm. And one reason is that it's very difficult actually to account for the well, this is a good question. The one reason is that it's difficult to account for the sheath effect. The probes are not far enough from the base of the satellite. They're still in the sheath effect or in the electric sheath of the satellite. So that's it's very difficult to account for that. And also the other thing, and I think I had it in one slide, but I didn't mention it. It's the fact that probe measurements depend on several things. They don't only depend on density and temperature. If that were the case, it would be a lot easier to interpret probe measurements. But they depend on these two variables, density, temperature, but also the distribution of masses, the flow velocity, the floating potential, and probably other parameters that I can't think of right now. But at least there are these 5 parameters, and not all 5 parameters are measured. Maybe there are 2 or 3 parameters that can be measured, but the other parameters are not known. And yet the characteristic of probes depends on all these parameters. So one has to estimate these parameters either by guessing what they may be, or using some theoretical model, and for those reasons it's difficult to infer plasma parameters from probe measurements or even from front plate measurements. Let's see. Please go ahead and ask more questions. I'm looking for this paper. Let's see if I can find it. Yeah, let's look at the proof.
So, yes, with regards to the previous question, where you said that you would show the paper for the equipotential, for the curved equipotentials, the person who asked the question, he said that he would like to see the paper.
Yeah, here it is. So these are the equipotentials, and this shows two different orientations of the magnetic field that we considered. And of course, this is a truncated satellite. The real satellite is more, well, it's approximately 10 meters long, and this is just a small part of it. And it is sufficient for the purpose of studying the Langmuir probe and the front plate. Is this, I can make this bigger if, whoops, not too big, but okay, so let's, now it should be quite visible. Is that what you were looking for?
Hopefully, yes, sir. I think, yeah, the person has already replied that this is what they were looking for. We'll move on to the next question.
Okay.
Okay, there's a question in the chat box. assess the double probe system as current is limited to the ion saturation current for both positive and negative voltages. And looking at I1 and I2, if we write the V bias is equal to V2 minus V1 as a hyperbolic tangent, the equation I get suggests neither electrode is ever very far above floating. So if I want to sample more of the exponential electron portion of the characteristic, taking such system may be challenging. Can we take asymmetric double probe? And if yes, how would that affect the voltage? I think it would also be better if you read this.
Yes. Um, and does that refer to a particular slide, a page number? Yeah, this is the, in these cases, remember the expression that I wrote down for, I don't know, I forgot if it was above, that I wrote down for the, yes, this equation here, it is in the electron saturation region. The probe is biased positively, and the assumption is that it is sufficiently positive for this sum. VF is generally negative, for this sum to be well above kT over E, which is the temperature in electron volts. And that corresponds to the electron saturation region for which, according to OML, this equation gives a good approximation for the current as a function of voltage. I mean, it can be made more complicated, of course, but in this approximation that I mentioned, when this ratio is larger than unity, then that is a good approximation according to the OML theory. And I probably did not answer the question, but that's the best I can do, unless you want to reformulate the question. Okay, can RBF regression method used in measuring plasma in fusion reactor? Well, there's nothing magic about RBF. It's just an interpolation or a regression method. But if there is a relation, there has to be a relation, because some people use neural networks, for example, or regression methods when really they shouldn't. But if there is a relation between a quantity that we want to measure and some observable, then yes, we can always use a regression technique, whether it's RBF or neural network or others. There are other such techniques. But the ones that we have explored are RBF and neural networks. And so I wouldn't go as far as saying that we can generate an equation of state for the plasma. The equation of state for the plasma is, I mean, in the lower ionosphere, it's very well described with the ideal gas law. If I pivots are points where we want our fit to work. Yes, that's correct. How would one go about selecting these? Yeah, that's a good question. What we do is, let's see if I can go back to the presentation. I think it was here. Yeah, so you see, actually, let's go here. You see, we have all these points here for the for the possible densities and temperatures in the ionosphere. That, as I said, it was generated with the. Sorry.
No, we cannot see the presentation.
You can't see my presentation?
No, it's visible. It is.
Well, here it says that I am presenting I can stop presenting and present again. Present my entire screen. Select the window, entire screen, allow. Can you now see my presentation? You should be able to see it in just a second.
Yes, we can.
Okay, so let's go. You can see that?
Yes, yes, we can.
Okay, great. So you see, in this case, where all the data points were synthetic data points, and those were obtained with the International Reference Ionosphere Model, which is a statistical model based on observations and model predictions, a combination of these two. We have, it doesn't show here, but we actually used thousands, tens of thousands of points to sample the ionosphere. But the strategy that we used to determine the best positions for the pivots is the following. We considered all, so I'll write it down here. So we considered all, n factorial over n pivots. So this is the number of pivots, n minus n factorial. So we considered all n choose n combinations of pivots, all of them, to and for each combination, we constructed a model and applied it to the full data set, calculated a cost function, a loss function or a cost function, they're the same. And the cost function was the maximum absolute relative error in the predicted density. That was our cost function. So for example, we consider this one as a pivot, then this one, and another one, and we did all the possible combinations and picked the one for, and in each case we assessed the skill of the model, and in each case, we calculated the cost function to assess the skill, and we chose the combination that gave us the best skill. That's how we did it. But you see, there's a triangular mesh here. The number of data points that we have in this scatter plot, well, it doesn't show all the data points. It only shows a small fraction. But in total, we had tens of thousands of points. This number here is much too big. We would still be doing the work, even though the work was done 2 years ago. I mean, we wouldn't be finished. This number is enormous. So what we did instead, we created a triangular mesh that contained all these points, and instead of doing all the combinations of 5 pivots among, let's say, 20,000 data entries, we considered all the combinations of 5 pivots among the vertices. And here I think there are 70, as I remember, there are 70 vertices, including the ones on the boundaries. So that was much more manageable. You see, this triangular grid covers the range of parameters that we found from the International Reference Ionosphere Model, and it was possible to do all these combinations here. And we picked the distribution of pivots that gave us the best skill for the RBF model. That's how we're doing it, and it's done now. At that time, it was done on a single processor. It was the starting point. It was the first time that we were doing this, but now we're running this on multiple processors using message passing interface MPI, and we can run this on 100 processors, and it goes 100 times faster. But it's still, this number here is still very, very large if the number of data entries is large, is several hundreds or even tens of thousands of numbers, then it becomes impossible. This approach, this direct brute force approach, does not work. But fortunately, it's possible to get good results even with a relatively small subset of a solution library.
So for the next question, we have, when talking about measurements of probe characteristics, you mentioned about theoretical and analytical approach. And also you briefly discussed about how the theoretical or analytical approach has limitations in terms of the assumptions we make, which will lead us, in many ways we overlook the physical and geometrical aspects of it. The physical part being overlooked is quite understandable. However, you did not elaborate on geometrical constraints which were overlooked in the analytical approach. Can you please elaborate on it?
Yeah. Let's go back to the most obvious case, which is this. Well, let's look at this. Analytically, with the orbital motion limited theory, we're working with just this sphere. It's just a sphere. There is no satellite at all. It's not there. What we have analytically is just this situation. We have a sphere in space and nothing else. But on a satellite, you have a satellite. The sphere is held by a post, and the post, as you can see in this illustration, it deflects particles. Not only the post, but also the satellite is attracting particles. It's attracting particles more than the sphere itself. So that's one aspect. Another aspect too, which is not quite as obvious, is okay. I think it's in the other place where, no, that's that's a different thing. Where is this? Let's see. Here. You see, I have a magnetic field here, and if the magnetic field, well, I have to tell you something basic about plasma physics, and maybe you know this already. Forgive me if I'm telling you something that you already know, but particles in a magnetic field gyrate around the magnetic field. And the lighter the particles, the smaller the gyro radius, the radius of gyration. So electrons gyrate around the magnetic field, and in the ionosphere, the magnetic field is such, and the energy of the electrons is such that the radius of gyration of these particles is approximately, I don't know, 2-3 centimeters. It's on the order of centimeters. So if you have a magnetic field which goes through the probe and which intersects the satellite, you will not collect the same current as if you had a magnetic field which goes through the probe and does not intersect the satellite, because particles gyrate around the magnetic field and they mostly follow magnetic fields. So as they gyrate, they follow along magnetic field lines. And let's say in this situation, you would not have currents coming from this direction here, but you would have current coming from that direction. And here you would have current coming from both directions, from this one, this direction, and that direction. And I realized that this is biased negatively, which means that it's attracting ions. So ions have a much larger gyro radius, but let's just assume that this is biased positively, which it is not in this illustration. It's biased positively, and then you would have electrons collected coming from this direction, from this direction, from this direction, but no electrons coming from this direction. So this is another reason why geometry matters. It matters because there are objects around, and these objects will perturb the electric field. They will create a sheet electric field that will compete. In this case, it's competing with the electric field of the probe, and also it can obstruct particles from reaching the probe. If we didn't have this thing here, we could have particles coming from far away in this direction and reaching the probe, but it's not possible because this object is there. Any more questions?
So I think
Okay, so
there's a last
there's
question.
one final question in the chat.
Okay. Okay, I'll switch to the chat. Let's see. May I take the liberty to ask a question not related directly to the topic being discussed? Dr. Marchand may choose to respond at the end of his lecture. So please, what existed before the Big Bang? I wish I knew. I mean, if I knew, I would immediately send a paper in Nature Physics, and become very famous. But no, I don't know. His take on multiverses, I don't know that either. So I'm sorry, I cannot answer. Not because I don't want to, but because I just don't know. Chair, the DOE of the paper you were presenting. I don't know if I have it. I think I do, but I would have to look for it. Maybe I can send it to one of you, and then you can share it. But it is being processed by JGR, Journal of Geophysical Research. So if you just search, wait a little bit because it's probably not on Google Scholar, but if you search for recendies, I'll type it here. Well, I type it. Can I type it on the? Yeah, I can type. So search for recendies and Marchand and if you do this, not now, but if you do it in a little while, then you should get a link to the paper. And JGR is open access, so you don't have to worry about having a subscription or having your institution have a subscription. You should be able to access it freely. Are there more questions or comments?
So I think there are no more questions. So I would like to take this opportunity to thank Dr. Richard for taking your time to come here and deliver this very interesting talk. I will now hand over to Dr. Harish Kumar to say a few words.
Okay.
Well, hi everyone. Hello, Professor Marchand. Okay, I think it's morning on your side, and it's quite late on our side. So it gives me a pleasure actually that I should actually propose a vote of thanks for this event, and to everyone whoever is present here and participated in the organization of this event. I would like to first thank Professor Richard Marchand for accepting our request and delivering this year Ranjan Roy Memorial Lecture to us. Special thanks to Mr. Anjan Roy, brother of Ranjan Roy, for participating in the event and sharing a few words regarding Ranjan Roy. I would like to thank our principal, HOD, colleagues, students, and student members for participating in this event. Special thanks to Physics Society members, executive as well as non-executive members, volunteers, for putting so much effort in organizing this event and making it successful. Last but not the least, I am thankful to the beloved audience for making this event successful. Once again, I thank one and all present here. Once again, thank you to Professor Marchand for delivering this talk. Thank you. Thanks a lot.
Well, thank you for the invitation. It was a pleasure to address your group of students.
Thank you, Professor.
So the session ends here. I would like to thank everybody for attending the session. Thank you.
Okay, thank you. Bye.
Thank you.
Bye-bye, Professor Marchand.